Now this is going to be about 2018 question 5, and we're going to focus on part 4 of D. Okay, so we're going to focus on the calculation in part 4. Okay, so a piece of fossilized yew from a tree that was alive about 6,000 years ago was excavated from Bura Bog, County Offaly. When a tiny fragment of it was analysed, it was found to contain 1.5 by 10 to the 12 carbon-14 atoms. Explain why the fragment of the yew must have contained 3 by 10 to the 12 carbon atoms 5,730 years before the analysis. Okay, well, that was pretty simple. It's because the half-life of carbon-14 is 5,730, so 5,730 years ago there was double the amount of carbon-14 atoms as there is now. So if there's 1.5 by 10 to the 12 carbon atoms now, 5,730 years ago there was double that, so there was 3 by 10 to the 12 carbon-14 atoms. So it's because 5,730 is the half-life of carbon-14. Okay, explain. Sorry, that's the bit we did. What mass of carbon-14 did the fragment contain? 5,730 years before the analysis. Okay, so for this, we're going to write down what we know from the question. So we're trying to find a mass. Okay, and at the moment we have the number of atoms that we have now and what we had originally. So we had 1.5 by 10 to the 12 carbon-14 atoms now. We have 3 by 10 to the 12 carbon-14 atoms originally. It said the tree was about 6,000 years old, so it could be that it was 5,730 years old. Pretty close in length, in given that period of time, when you're talking about thousands of years. Okay, and 5,730 is the half-life of carbon-14, so we know that there's 3 by 10 to the 12 carbon atoms originally. So this part of the question, what mass of carbon-14? Alright, it's asking for a mass. It's asking for the mass of the carbon-14 originally. Okay, so when they're saying 5,730 years before analysis, they're asking originally what mass of carbon-14 did that fragment contain. Okay, so at the moment we only have how many atoms there are, and that's 3 by 10 to the 12. So to go from number of atoms to mass, we're going to need two formulas. The first of those is this one here, the first one. So usually the number of moles multiplied by Avogadro's number will give you this number of atoms. In this case we have the number of atoms, so if we rearrange this to give us the number of moles, which is what we want, it's going to be the number of atoms divided by Avogadro's number is going to give us the number of moles that we want. And then to go from moles to mass, okay, we have a formula that contains both of those as well. And usually what we'd be saying would be that the number of moles is equal to the mass over the relative mass, or the molecular mass. So again, we have our number of moles. We want to find mass. So again, we just rearrange to what we want to find. So mass is going to be the number of moles multiplied by the relative mass. Okay, so once you have them two formulas, it isn't too difficult. It's just the rearrangement of them formulas, and I suppose spotting that that's what you have to do. So it's going to be 3 by 10 to the 12, because that's the number of atoms we have at the moment, or that's how much you had originally, divided by Avogadro's number, so 6 by 10 to the 23, and that gives you 5 by 10 to the minus 12 moles of carbon-14 originally. Okay, so that's our number of moles, and then you multiply by the relative mass. Okay, here, because we have carbon-14, our relative mass is 14. Usually the relative mass of carbon is 12. But in this case we have a radioactive isotope of carbon, which is carbon-14. So our mass in this instance is 14, because we have 6 protons and 8 neutrons. So it's going to be 5 by 10 to the minus 12 multiplied by 14, and that gives us a final answer of 7 by 10 to the minus 11 grams of carbon-14 originally, which was 5,730 years ago. Okay, so I hope that is clear. Right, it's just spotting really what you have to do there with your two formulas there at the end. Okay.